Lesson 6 is geometric sequences, and just to review really quick, we've learned about arithmetic sequences, and arithmetic sequences are sequences where we're adding the common difference to get to the next term. Geometric sequences will be a little bit different. So starting in 6.1, what is a geometric sequence? Geometric sequences are defined by a sequence of numbers in which each term in the sequence is produced by multiplying the previous term by a common ratio r. So arithmetic sequences are adding to get to the next term. Geometric sequences are multiplying to get to the next term. And then in like arithmetic sequences, sometimes it looks like we are subtracting to get to the next term, but we really just classified it as like adding a negative number. And similar to that, geometric sequences will sometimes look like we're dividing to get to the next term, but instead of dividing, we can actually think of it as like multiplying by a fraction. So for example, if I were dividing by 2 to get to my next term, I could rewrite that as multiplying by 1/2, and that would be my ratio because dividing by 2 and multiplying by 1/2 has the same outcome. And then the domain of a geometric sequence is the natural numbers, the set of natural numbers, which are like the numbers that you would like count with. So if you started counting, you'd be like 1, 2, 3, 4, and so on. It's like no negatives, no decimals, or anything like that. And that's because the domain of these are going to be the term number. So like you would have term 1, term 2, term 3. You wouldn't say like term 1.5 or anything like that. And then for geometric sequences, something that's a little bit different than arithmetic is they cannot have a term that's 0. And that's because with geometric sequences, because we're multiplying, if one of my terms was 0, and then I multiplied by my common ratio to get to the next term, well, 0 times anything is 0. So this would be a 0, and then it would just continue with like multiplying to get 0 again. So it really wouldn't be much of a sequence at all, it'd just be really a list of zeros. So you won't have any terms that are zeros in a geometric sequence. Okay, so a couple of examples of geometric sequences are up here. So the first one is 1, 2, 4, 8, 16. So you can see that each number is like doubled, or to get to the next term, you're doubling the previous one. So like from 1 to 2, we're multiplying by 2. To get from 2 to 4, we're multiplying by 2 again, and then 4 to 8 multiplied by 2, and 8 to 16 multiplied by 2 again there. So our common ratio for that first one would be 2, because that is the number that we're multiplying by to get to the next term. And then for the second sequence, it's 16, 8, 4, 2, 1. So you can see each one is getting cut in half. So sometimes, like, yes, we are dividing by 2 to get to each term, but our common ratio that we're trying to find is like, what are we multiplying by to get to each term? So if you recognize that like multiplying by 2 is the same thing, dividing by 2 is the same thing as multiplying by a half, then you could just change it like that. So like 16 times a half would get me to 8, 8 times 1/2 would get me to 4. But if you ever have a hard time like thinking about how to convert it from like division to multiplication, to find r of any ratio, you can take one term and divide it by the previous term. And it doesn't have to be the first two, it can be any two. So I can do like these two. And if I take one term and it'd be 1, and then divide it by the previous term, it'd be 1 divided by 2, or 1/2, and that would be r. So you can always do that. We'll kind of do that throughout some of the examples. To find r, you take a term and then you like divide it by the previous term. You kind of work backwards from like multiplying, you would be working forwards. Okay, so example 1, analyze the shape of the graph of the geometric sequence and find the common ratio r. So when we did an arithmetic sequence, all of our like points were kind of in a line. You don't need to draw this, but they would end up being a straight line like this, and all the points would fall along some sort of straight line. But you can see on this graph, like the points are kind of growing and they're like curving. And that's because a geometric sequence represents something called like exponential growth, where it's growing really quickly instead of at like a continuous rate. So this would be something called exponential growth. So exponential growth is how you describe like really all geometric sequences. They're growing at an exponential rate. And then if I wanted to just like find the common ratio. You can find it directly from the graph. Remember that when you look at a graph, the like x coordinate is the term number and the y coordinate is like the term value. So if you wanted to find r just from the graph without like really rewriting the sequence, you would have to look at how the like y coordinates are changing. So like the y coordinates are going from 1 to 2 to 4 to 8 to 16 and then to 32. So to get from one y coordinate to the next, you're multiplying by 2. So 1 times 2 would get to 2, 2 times 2 would get to 4, 4 times 2 would get to 8, 8 times 2 would get to 16. We don't have to worry about the x coordinates here because remember the x coordinates are just the term number. It's like term 1, term 2, term 3, term 4, and so on. If you ever have like a difficult time with just the graph itself, remember that you can kind of rewrite it as just like a list in brackets. So if we were to do that, we would start at the like first term, which is just the y coordinate from that first point. So it would be 1, and then term 2 would be the y coordinate from the second point, 2, term 3 would be 4, term 4 would be 8, term 5, 16, and then term 6 would be all the way up here in 32. And then we draw the dot, dot, dot to show that it keeps going from there. So you can always do that if it makes it easier to find the common ratio r. So now that we have like the list of numbers in front of us, the common ratio is going to be like, what do we have to multiply the term by to get to the next one? So like from 1 to 2, from 2 to 4, from 4 to 8, each time we're multiplying by 2. So my common ratio r would be 2. And then same thing here, if you ever like can't tell what you have to multiply by, you can work backwards and you can divide one term by the previous term. So in this case, I could do like 2 divided by 1, which is 2. Or I could even do like 4 divided by, I said that backwards, 8 divided by 4, which is 2. I could even do 32 divided by 16, which is still 2. Okay, so moving down to example 2, imagine you have a lemon tree and you track the number of lemons it produces each year in the following table. The input is the year. It's also going to be our term number in terms of like sequences. And the output is the number of fruits. So write a geometric sequence and find the common ratio r. So the like tops of our table are always going to be like, without any context, they're the term number. Even though this gave it like a bit of context. But in this case, our term number is like year 1, year 2, year 3, and so on. And then the bottom of our table, like the output of our table, is always going to be the actual like value of the terms from the sequence. So you can leave it in the table if you want, or you can rewrite it in brackets. It really just comes down to personal preference. If you wanted to rewrite it in brackets, you would just do the bottom row, just the output of the table. So it'd be 1, 3, 9, 27, and then 81. And then now if we wanted to find r, you could go off the table or off like the bracket set. Just what number do I have to multiply by to get to the next term? So I'm going from 1 to 3 to 9, 27 to 81. So each time I'm multiplying by 3 every single time, because 1 times 3 would get me to 3. 3 times 3 would get me to 9. 9 times 3 would go to 27, and 27 times 3 would go to 81. So r would be 3. Same thing here, if you ever can't find r that way, you can just work backwards and divide one term by the term ahead of it. So we could do 81 divided by 27, which is 3. We could do like 9 divided by 3, which is 3, or even 3 divided by 1, which is 3. Okay, moving down to 6.2, this is writing recursive formulas for geometric sequences. So recursive formulas, we've talked about them before. Those are the ones that you have to write in 2 parts, where you state the first term and then there's the rest of the rule. So we've written down like a recursive formula before, but we wrote it down for arithmetic sequences. So it will be a little bit different for geometric sequences. So recursive formula of geometric sequences. So the first part is the same. We're still going to state the first term. So whatever the first term is, we'll go here. And then after that, the second line is an equals an minus 1 times r, and r is the common ratio. Okay, there's a few notes over here of just what each thing means. This is like, should look a little bit familiar at this point because we've talked about it in a few lessons, but an is just representing the nth term of the sequence. So like if you wanted to find the 20th term, you would find a20, or like the 30th term, you'd find a30. An minus 1 just means the term before the one you're looking for. So like if you're looking for term 10, then an minus 1 would be a9, like term 9. And then r is the common ratio. That's what we've been doing, like kind of up through the notes until this point. Okay, so example 1, write a recursive rule for each geometric sequence. I'm just going to go ahead and like copy the formula down really quick, and then we'll just take out each letter that we need to as we find out what it is. So it'll be a1, we'll leave that blank, and then the second part is an equals an minus 1, and then times r. So we just have to find our first term here, and then we have to put something in for r right here, and we don't need to put anything in for an minus 1, or anything like that. So if we look at example 1, a1 is just always the first term in the sequence, so whatever comes first, so a1 would be 1, so I'm just going to put a 1 there right away. And then for r is the common ratio. How do I get from one term to the next? So I'm going from 1 to 3, I go from 3 to 9, from 9 to 27, so I'm multiplying by 3 every single time. So that means that r would be 3, and that goes in there. So I'm just going to take that r out and drop the 3 in. And then that's all we need to do for like writing a recursive rule, so we're done there. So a1 equals 1, and then the second line is an equals an minus 1 times 3. Okay, so same thing. I'm just going to copy this one over, and I'll switch the letters back. Okay, so a1, our first term, is going to go right there, and then this was an r initially, so our r value will go there. Okay, so looking at our table, so from our table, the input values are like all of our term numbers. So, and it's really good if you're like not comfortable with that right away to just leave the note for yourself each time. So if you go back and look at your notes, it makes sense. So input is term number, and then output is the term value. Hopefully those are starting to get like a little bit more comfortable at this point. So term number is the top, the input, and then term value is the bottom, the output. Okay, so a1 is just our first term. So you can see like term 1 is that first slot on the table, and the actual value of it is 2,744. So we're going to put 2,744 in for a1. And then now we just need to find r. So this is a good example of like knowing kind of the backup way to find r in case it ever comes in handy. So there's a couple of different ways that we can approach it. You really just need to pick, or let me backtrack a little bit. Okay, so what I mean by like knowing the backup way is r is like what we're supposed to multiply by to get to the next term. And I don't know what you have to multiply 2,744 by to get to 196. Like, I just don't know it. And if you do, more power to you, but I don't know. And then like same thing, I don't know what you have to multiply by like 196 by to get to 14, and so on. So if you ever are not sure what r is, you can take any two consecutive terms in the sequence. So consecutive means next to each other. So I can do like these two and divide them. So you would do like the second term divided by the first term. So for r, could do 196 over 2,744. But you also don't have to pick the first two terms. You can pick any two consecutive terms. So there may be some ones that might be like a little bit easier to reduce, or maybe already reduced for you. So like, for example, these are consecutive. I would take, this is like term 3 and term 4. you always take the second one and you divide it from the one before it, so you're working backwards. So like I could do r equals, it'd be 1 divided by the term right before it, which is 14. So that's actually like what this would end up reducing to, but I don't have to do the hard work now of reducing it. It's already reduced, 1 over 14. So r equals 1 over 14. So I'm going to take this r out and put in a 1/14. So my recursive rule is a1 equals 2,744, and then an equals an minus 1 times 1/14. So for finding r, if you're not sure right off the bat, pick any two terms that are right next to each other, and you would always kind of work backwards. So take one term and then divide it by the previous term. So 1 divided by 14. Okay, so for C, this one's a little bit different. We're still going to write a recursive rule. Let me copy this down actually and fix it. So this is going to be our A1 right here, and then this will be our R. Okay, so for C, the reason it's different is because you can kind of see like we don't have the full sequence, right? So C says A3 equals 64 and A4 equals 32. So they don't give us like the first term like the table did or the sequence from part A. We don't have a whole lot of information, but we can use what we do know to fill in what we need. So when you have a problem like this, I highly, highly recommend kind of just like creating a fill in the blank sequence. So what I mean by that is like, this is term 3, this is term 4. So I'm going to do 1, 2, 3, 4. And I know, so this is going to be, I'm going to put the term numbers down here. This will be term 1, term 2, term 3, term 4. So I know that term 3, A3, which is term 3, is 64. So I'm going to put a 64 here. And then I also know that term 4 is 32. So I'm going to put a 32 here. And then as long as I have 2 consecutive terms, I can find R. I just have to take one term and divide it by the one in front of it. So to find R, I would take 32 and I would divide it by 64. So do 32 and then divide it by 64. So it's important to note it's not always like the bigger number divided by the smaller number. You have to take one term and divide it by the term in front of it. So 32 over 64. And then now we need to reduce it. So if you like know how to reduce it in one step, nice. I'm going to show you like if you're not exactly sure how to do that, how you could really do it in a few steps. So we just need to think of any two numbers that like divide into 32 and 64. So even like if you can't think of any, they're both even. So you could start by dividing by 2. I'm going to divide both by 8. So I'm going to divide both by 8. You have to do numerator and denominator, the top and the bottom. So 32 divided by 8 is 4, and then 64 divided by 8 is 8. And then those still have a common factor, so I can keep dividing further. So you can divide 4 and 8 both by 4. And it's okay to divide a number by itself as long as you're doing it on the top and bottom. So 4 divided by 4 is 1, and then 8 divided by 4 is 2. So we would get R equals 1/2. So that means that the number that we are like multiplying by, let me shrink this just so I can write under it. The number that we are multiplying by to get to each term is 1/2. So it's like times 1/2, times 1/2, and then times 1/2. But that's as if we're like increasing in terms, like we're going to the right. If I kind of wanted to work backwards and go down in term number, I couldn't continue to like multiply by 1/2. I would have to pretty much do the opposite of that, which would be like multiplying by 2. And if that's kind of tricky, think about how like if I wanted to go backwards from 32 to 64, I would have to multiply 32 by 2. So to go backwards here, I'd have to multiply by 2. I would have to go and multiply by 2 here. And that's because we have to remember that like multiplying by 1/2 is the same thing as dividing by 2. So I would like to go to the right, I would divide by 2. And then to go to the left, I would have to do the opposite and multiply by 2. So I would do like 64 times 2, that would be 128. And then 128 times 2 would be 256. So if we are doing like one thing to go to the right, in this case it's multiplying by 1/2, I have to kind of reverse that to go left. This one's a little bit tricky because it's like multiplying by 1/2, we have to think of it in terms of like it's the same thing as dividing by 2. And then to go backwards, I would do the opposite of dividing by 2, I would multiply by 2. But we have to do that because we have to know the first term to be able to write a recursive rule. And that 256, that's our A1, that's our first term. So now that we've kind of done all that, we are done. We just have to take the values that we know and put them into the formula. So A1 is 256. And then for R, we found out R was 1/2. So A1 equals 256, and then AN equals AN minus 1 times 1/2. Moving on to 6.3. 6.3 is explicit formulas of geometric sequences. And remember, for explicit formulas, those are the ones that come in just one part as opposed to recursive is 2 parts. And explicit formulas are generally better for finding any term of a sequence. Like if you wanted to find the 100th term of a sequence, if you used a recursive rule, you would have to find 1 through 99 first. And if you used an explicit rule, you would be able to get there right away. So the explicit formula for geometric sequences is AN equals A1 times R raised to the n minus 1. So A1 is still our first term, R is still our common ratio. That's like what we're multiplying by to get to the next term. And then that little n minus 1, remember that n is always like the term number. And that little n minus 1 is going to be an exponent. Okay, so example 1, find the 4th term of the geometric sequence represented by AN equals 3 times 5 raised to the n minus 1. So it tells us to find the 4th term, and we know that n represents the term number, so n is going to be 4. So we're not writing the rule here, so we don't need to put anything in for A1 or for R, it's already there for us. Like A1 would be 3, that's the first number, R would be 5. We just need to take our like n equals 4 and put it in for n, and then simplify to find out what the 4th term of this sequence would be. So when we go to substitute that 4 in for n, we're also going to put it right there. And so it'll be an A with a little 4, and that just means the 4th term. So A4 means the 4th term, and it'll be equal 3 times 5, and then raised to the n minus 1. We're going to put 4 in for that n, so 4 minus 1, and close parentheses. And then for these problems, it's really important to follow order of operations to make sure you get to the correct answer. So order of operations, that's like PEMDAS or GEMS, depending on how you learned it. But the first letter in each, the P is for parentheses, the G is for grouping symbols, which means parentheses. So we're going to subtract inside here first. So we'll do 4 minus 1 as our first step. So it'll be A4 equals 3 times 5, and then raised to the 4 minus 1, so 3. You can leave the parentheses on at this point, or you can take them off. And then the next letter in each of the like order of operations is E, and that's for exponents. So next we'd have to simplify the exponent part. So it would be 5 to the 3rd power. And 5 to the 3rd power means 3 5s being multiplied together. So that's what exponents are, is they tell you how many times to multiply the base, like the bigger number, by itself. So 5 to the 3rd power would be 5 times 5 times 5. So A4 equals 3, and then 5 to the 3rd power, 5 times 5 times 5 is 125. And then now that we've simplified exponents, we can go ahead and multiply together to get our final answer. So it'd be A4 equals 3 times 125, which is 375. So this means the 4th term in that sequence is 375. Okay, so moving on to example 2. I don't know why I wrote example 1 again right here, but this is example 2. Example 2, write the explicit rule for the sequence represented by the table and then change it into function notation. So we have our formula here. It's AN equals A1 times R raised to the n minus 1. So for our explicit rule, we have to find 2 things. We have to find A1 and we have to find R. We are not going to put anything in for n because this is going to be a rule that helps us find any number, term number in the sequence. So we just leave n as is. Okay, so A1 is always the first term in the sequence. You'll notice on the table, like all the input values are on the top. Those are all the term numbers. All the output values on the bottom, those are all the actual like term values. So A1 is going to be under like term number 1, and the actual value of it is 2. So A1 would be 2. And then we have to figure out what R is. So R is how we get, sorry, it keeps getting in the way. R is how we get from like one term number to the next. So to find R, we're only looking at the output values because those are the actual values of the term. Again, that top row is just telling you what the term number is. So for R, we're going from 2 to 8. We go from 8 to 32. We go from 32 to 128. So if you recognize that you have to multiply 2 by 4 to get to 8 and 8 by 4 to get to 32, that's going to give you your R value of 4. If you don't recognize it, remember you can take one term and divide it by the previous one. So we could do like say 8 divided by 2. That would give us 4 also. Or you could even do like 32 divided by 8, and that's also 4. So we know that A1 is 2, we'll put that in there. And then we know that R equals 4. We'll put that in there. So it'll be AN equals A1, which was 2, and then times R, which was 4, and then raised to the n minus 1. And again, we're not going to put anything in for n because we're just writing a general rule here. So our general rule is AN equals 2 times 4 raised to the n minus 1. And then the instructions also say to like change it into function notation. So function notation for explicit geometric sequences is as easy as just changing AN into f of n. So instead of AN, it would be f of n, and then everything else gets to stay exactly the same. So like 2 times 4 raised to the n minus 1. So 2 times 4 raised to the n minus 1. Okay, so it's just kind of important to be familiar with like both notations because you'll see some problems that will randomly like pop up the f of n in there, and you just want to recognize that it really does mean like the same exact thing, so not to let it throw you off.